This video is about simple multivariate regression. Simple multivariate regression is a beginning step into the world of regression analysis that has a variety of statistical tools that can do a lot of things for you. In this circumstance, we're just going to look at the most basic version of it so that you can answer basic questions in applied settings. In the previous videos that I've done, there are several that you will need to be familiar with, and you'll need to understand the information in them to be able to work with what I present here. There's a video on the framework for applied statistics so you understand what I'm trying to do and what I'm not trying to do in these videos. There's an introduction to the free statistical software package that I'm using. It doesn't have all the bells and whistles and some of the great features that paid statistical programs have, but it is something that a low budget circumstance can use to answer statistical questions. There's a video on shape, strength, and significance, which will help you understand how I tend to make sense of statistical results so that you can answer questions. There's a video on central tendency and dispersion. There's a particularly important video for this one on correlation and bivariate regression that lays the groundwork. And in fact, we will refer back to the material in that video to be able to use the material in this video. And then there's a video on specification, which is a way of trying to make sense of how statistical controls affect our ability to answer questions. Now, specification as a term is used more commonly to just say, how do variables relate to each other in a model? Which variables belong in the model, and where do they fit into the model relative to each other? But the way that we test specification of variable placement is through multivariate analyses. So generally speaking, I'm using the term specification to refer to what we learn when we institute statistical controls in our analyses. The grid that I use for choosing statistical tools is an oversimplified grid that will guide you into choosing the tool that is usually right most of the time for your setting. Then, once you've run those results from that tool, I suggest that there are a few things you need to be looking for to be able to answer the questions. And then I give 5 guidelines in this framework that try to introduce you to ways to avoid making mistakes and still answer the real question when you present or write up your results. The overall grid then is meant for a more simplified applied setting, but lays a good foundation for any advanced statistical work you might do later. I'm going to start with these analyses questions. I'm going to start with, is the percent of the population saying prostitution is never justifiable related to government spending, GDP per capita, or Human Development Index value? Then, how much is the percent of the population saying prostitution is never justifiable related to government spending, GDP per capita, or HDI value after we've controlled for the other independent variables? And third, how much is the percent of the population saying prostitution is never justifiable related to government spending, GDP per capita, and HDI collectively? The first one is discussed in the correlation video. I won't unpack it here, but you will have needed to answer that question before you can go on to answer the rest. The second question that asks how important is each independent variable after controlling for the effects of the other independent variables is an example of a net effects kind of multivariate analysis. And the third question, which asks how much explanation do we get of the percent of the population holding this view when we collectively look at the effects of all of these independent variables together, this is an example of a collective effect multivariate analysis. So the data that I'm going to use is going to be the world data set that we've been working with throughout this series of videos. The world data set is basically meant to introduce you to countries of the world in quantitative ways and get you thinking about using cases that are different than just individuals, which most of us see more intuitively. The variables I'm going to work with, all of which have been used in previous videos, look at the fourth wave that was done in a series of countries about when is prostitution justifiable, and for each country we have a number that says the percent of the population that says it's never justifiable. We have a measure on government spending that's been discussed in previous videos, a measure of gross domestic product per capita, and a measure of the Human Development Index values from 2018. All of these variables have been explained and unpacked in previous videos. In the choosing grid, we have to first decide if we're doing one variable analysis. We're just going to take each of these variables by itself and look at the results in it. Or if we're doing two variable analyses, where we want to basically take an independent and connect it in pattern analysis to the dependent variable and see if they're related. Or if we're doing multivariate analysis, where we have independence and a dependent, but we also statistically control for the effects of some variables while looking at the relationship between other variables. In this circumstance, clearly we're doing simple multivariate analysis. So any statistical tool we use is going to be in this row. The dependent variable is the percent of the population believing that prostitution is never justifiable. This is a scaled variable, and so we end up in this column. As we move down the column, we find that we have to decide if the independent variable is categorical or if the independent variables are interval or ratio. All of our independent variables in this example are interval or ratio, so we end up in this column. When we grid that out, we end up with multivariate regression. And so we need to look to answer questions at the shape, the strength, the significance, and the specification, the way I've described what those are in previous videos, to be able to answer our questions. Now, there are some assumptions that happen when we're looking at multivariate regression. First, we assume that none of the cases have non-valid or quote-unquote missing data. I've cleaned up this data set so that any data values that may have stood for this country doesn't have a value for this variable, or this is a number that indicates something unusual for the country that isn't really about what the variable measures, all of those have been removed. It assumes there are no serious outliers. In the last video, I showed you an example of a bivariate outlier in the correlation scatter plot that was shown. And so this one, I'm going to not include variables that have those kinds of outliers. There is an assumption of linearity, but I put it in quotes now because we have more than two variables related. It's beyond the scope of this video to explain it, but when we add 2 or 3 or 4 independent variables to the model and we run the mathematics, we're not just talking about a straight line. That's what we could have if we have an x-axis variable and a y-axis variable, and then we have a straight line, best fitting line as our prediction model. That's what we did in bivariate correlation. But in this circumstance, if we have 2 or 3 or 4 independent variables, or however many we have, we actually end up with a multi-dimensional best fitting project. And that is still assuming a certain kind of flat surface, but it begins to boggle the mind to be able to conceptualize a 3 or 4 or 5 dimensional flat surface. So we're just going to say there is still an assumption of linearity. Curved relationships are not seen, but we're not going to try to unpack that any more than that. Now we have a new assumption here that there will be no multicollinearity involved in the model. I'll explain that in a moment, but basically it's saying our independent variables cannot be strongly related to each other. This isn't to say that an independent variable cannot be strongly related to the dependent variable. That's fine, that's great. Don't worry about ever seeing an independent variable connected strongly mathematically to the dependent variable. But when independent variables are strongly related to each other, there's a problem using the mathematics of multivariate regression. These are parametric statistics, and so they assume normality and homoscedasticity, as has been discussed in previous videos. So multiple regression that we're using here is something called ordinary least squares regression. In the prior video, I showed a best fitting line and a scatter plot, and I talked about how you measure all those distances between the actual case plottings and the prediction line, and you add them all up. Well, what you really do is you take that distance, you square it, and you add them all up, and that's called the ordinary least squares. You want a line or a prediction plane or a prediction three-dimensional linear model. You want all of these prediction models to have the least error in correctly placing where the cases end up. And so ordinary least squares, least squared deviations. Now it's ordinary in the sense that you can have a variety of other versions of this that are beyond our scope here. Two-stage least squares, weighted least squares. So regression is a very robust and valuable tool, and we're looking at the most commonly used version of it. Whenever somebody presents you with regression results with no other name, they don't call it logistic regression or some other name, they just say here are the regression results. it is almost always ordinary least squares linear regression. All right, so in the specification video, I talked about how statistical controls can help us to do something called net effect analyses, something called collective effect analyses, something called interaction effect analyses, and can also help us to specify a causal model. Multiple regression does allow us to do net effect analyses. And so what we're going to look for when we look at some results is we're going to look for shape by looking at a direction of effect in the sign on what's called the beta. And the beta is the standardized slope. That'll be unpacked here in a minute. The strength is found from the actual number, the value of beta, or the magnitude. It ranges from 0 to some undefined upper limit, and we'll explain that in a moment. But in essence, like we did with R, where we looked at the sign and said, is it a negative relationship or a positive relationship? With beta, we look and we say, is it a negative or a positive beta? And like R, where we looked at the magnitude and we said, is it closer to 0 or closer to 1? In this circumstance, we're going to look at the beta and we're going to say, is it closer to 0 or is it a bigger number as it moves away from 0, because there's no defined upper limit. In significance, we're going to use a p-value associated with beta, and it works just like the p-values have always worked. It's telling us the probability that we would get the real-world results we did if, in fact, the null hypothesis was true in the real-world population data. So we're trying to find out a little test here to find out if we can reject the null and say, no, we really think something is probably going on in the population because we don't think the null is true. The probabilities are against the null being true. And then in terms of specification, what we're going to do here for most of this is we're going to compare the bivariate strength and significance to the strength and significance we find in the betas after controls. That's the net effect. Collective effects are also talked about in multiple regression, and this is the first tool in this video series that has had a collective effect measure. There is no shape reported. I'll unpack that when we get to the example, but there is no way to talk about direction of effect, because if we have 2 or 3 or 4 or 5 independent variables, some of them are causing the dependent values to go up, some of them are causing the dependent values to go down, and so collectively what they're doing can't be described as up or down, except in a net sense, because we have to take all of them into account. So collective effects is just summing up how much effect overall is being explained by this set of independent variables, and we can't have a direction. So there's no shape reported in collective effects for multiple regression. Strength is reported by the magnitude, the actual value, the size of the number, of a tool called R squared. Now it's capital R, it's the multiple correlation coefficient, and then the multiple correlation coefficient is squared, thus multiple R squared. This ranges from 0 to 1, like so many tools we've looked at. So as you get closer to 0, the collection of independent variables are explaining nothing, and as you get near 1, the collection of independent variables are explaining all of the variation in the dependent variable. There's a significance p, a probability value, just like all p-values. This one comes from an f-test. It is another analysis of variance, just like what has been used in previous examples and other videos. There's a different mathematics of how we decide what pieces go into the f-ratio, but it's the same f-test, and so there's a p-value from that f-test, and it is the one that tells us the probability that we could get the real-world multiple r squared we have, if in fact multiple r squared was equal to 0 in the population, the null hypothesis. And then there's specification. There's no additional after controls information reported in collective effects. It is possible with simple OLS regression to look at interaction effects, but it's beyond the scope of what I'm going to do here. But any basic stats book that talks about dummy variables, just go looking for one that talks about dummy variables, and you'll find out how to put in categorical variables. But usually I use that as kind of the baseline. Once they start talking about that, they usually also talk about other things. Another thing that could be talked about is interaction effects, and interaction effects of how two independent variables or any pair or three or four independent variables collectively interact and affect each other's effect on the dependent variable. Starts getting a little complicated. We won't look at interaction effects here, but it is possible in simple multivariate regression, or just a little beyond simple multivariate regression, to look at interaction effects. And in terms of specifying the causal model, in terms of deciding which variables go where in the model and have arrows pointing at other variables, all of these results, particularly the net effects and interaction effects, help us to specify a model. We're just not going to go that extra step in this video series to look at how we would interpret it, because it involves a conceptual step quite a bit beyond what we're doing with our basic applied statistical work here. So let's jump over to the analysis program and let's take a look at how we would do multivariate regression. I've already opened the world data set that we've been working with, and so I'm going to go into the regression option here, and I'm going to choose first correlation. Now, that's not our point here. We want to look at linear regression, but I'm going to start with correlation because we need to have the results of the correlation matrix to be able to use the results of the multivariate regression to make sense of what we've learned after statistical controls. Our dependent variable is the 656th variable in this data set that I've put together. So I'm going to put it first because that makes it easier to read the results related to that once I get the correlation matrix. And then we have independent variables related to number 101 is government spending, 118 is GDP per capita, and 124 is the Human Development Index rating for each country. All right, so here we have the correlation matrix. We're going to need that to be able to make sense of the multivariate. Okay, let's set that aside. We'll come back and look at those results in a moment. Now, what we want to do is we want to then go ahead and do linear regression. And again, we want to choose the dependent variable as 656. We're going to use the same enter method that was talked about in the previous video for bivariate regression. It's the most commonly used version of OLS regression. And then we're going to put in our independent variables, starting with 101, government spending, then 118 for the GDP per capita, and then the HDI value. Okay, now that's how you would run it. You don't really, with this particular tool, need to do anything more. You don't need to go in and specify model or statistics or options or plots. You can basically work from what we have there on the screen. We're going to discover that there's a problem here. I'm going to unpack this as we look at the results in just a moment. But there's a problem here. There's a violation of the multicollinearity assumption. And so we're going to have to remove a variable from our analysis. I'll explain why in a second. But basically, we need to take GDP per capita and we need to make it go away. And these are the results that we're going to work with. But that's how you would actually run it in JASP. Okay. So here's the correlation matrix. For the net effects, we're going to have to know what the bivariate correlations were. So we can see that prostitution view in the countries is related strongly to government spending in the countries with a correlation coefficient that's 0.6. It's a positive relationship. Those countries that tend to spend more are countries that also tend to have a larger percent of the population that says prostitution is never justifiable. Now, we don't care now about the GDP per capita because I've already removed it from the multivariate regression, and I'll explain why in just a second. But we do care about the Human Development Index value, and that again is a strong, a 0.7, a very strong relationship between HDI value and view of prostitution, but now it's a negative effect. So now we see that as countries have higher Human Development Index values, where the population has more education, higher average income, longer life expectancy. Where that's true, there tends to be a lower percent. As HDI goes up, negative effect, prostitution goes down. The view of prostitution is never justifiable drops. Strong negative relationship. Both the government spending and prostitution view and the HDI and prostitution view results are statistically significant, with P being less than 0.001. Okay, we know that. We're going to use that in a moment. Now, we've never used this other side of the correlation matrix, but these values tell us how each independent variable relates to the other independent variables. And as I said before, no multicollinearity is saying that we cannot have any two independent variables strongly related to each other. So we need to make sure that none of these variables are correlated beyond, say, 0.59. So if I have a 0.6 or higher, then I need to be concerned. So what do I have here? I have a 0.409. Doesn't matter the sign. Negative or positive is direction of effect. We're just looking at strength of relationship here. 0.409, no problem. 0.473, no problem. Oh, 0.749. Too much. Too much correlation between these two variables, between GDP per capita and HDI. Now, this isn't terribly surprising because HDI has a measure of average income. And average income and consumption and all those things are tied to the GDP per capita, right? Income levels and consumption are basically related in a larger economy. So we're not shocked to find these related, but that's a problem because it means that these two things are, to a certain extent, measuring some of the same economic realities. So one of them has to go. Which one should we remove? You could, if you wish, you could look at the bivariate results and you could say, well, I want to keep in the stronger of the two when I looked at the bivariate results. So when I tried to find out how they were related with the view of prostitution, I saw that GDP per capita had a 0.62 strength and HDI had a 0.701. And I might say, well, I'm going to keep 0.701 because I want to keep my best predictors in this model. That's legitimate. You could do that. You also, and maybe you really should, think about theoretical or practical understandings of how these things might be related and which ones matter. So I might say to myself, if I'm trying to explain the percent of the population that says prostitution is never justifiable, do I want a measure of their basic GDP as something that I theoretically believe is related to cultural views of prostitution? Or do I think that a measure that collectively looks at education levels, looks at income levels, and looks at life expectancy might be more important for why I think prostitution views change? And if you unpack your own explanation for what you think matters, then you may decide to keep one or the other instead. Generally, if you can come up with a theoretical or practical explanation, a making sense of the world that helps you to figure out which variable should be left in, do that. But if you can't, then keep your stronger predictor. In this circumstance, I believe both of those tell me that the HDI measure is a better choice to keep in my model than the GDP per capita. And so GDP per capita is going to drop out. Now, here are the linear regression results that we just ran after we removed GDP per capita, because multicollinearity said you can't have it and HDI both in the same regression model. So if we're going to look at net effects, we can ignore the top two tables. The top two tables tell us about collective effects. The bottom table tells us everything we need to know for the net effects. So you remember from the video about bivariate regression, that was the same one that covered correlation, that these numbers here under the arrow are the unstandardized slopes. So as you have a 1 unit increase in government spending, whatever that variable is counted in, as you have one more unit of that, you will have a 0.193 increase. It's a positive number, so it's an increase. You'll have a 0.193 increase in the percent of the population that says prostitution is never justifiable. Whereas for Human Development Index, as you have a 1 unit change up, always up when you say the sentence, as HDI goes up 1 unit, the value on percent of the population that says prostitution is never justifiable will go down by 88 percentage points. Okay, now HDI is measured on a 0 to 1 scale. So when you say go 1 unit, 0 to 1, you're talking about making the entire leap of the scale. And that's why it's driving down the population percentage down by such a massive amount of 100%. So that's fine. But you see, I want to figure out which of these matters more. And I'm comparing on totally different scales. The government spending is on a 0 to 100 scale that's constructed out of something about the proportion of GDP that is spent by the government in different ways. And HDI is this combination of education levels of the population, the average income levels, the life expectancy averages, and it combines it. And I go, this is like comparing soup and nuts. One's a fluid, one's a solid. I don't even know how to compare these. It would be like saying, what is the factor that most affects a student's performance in school? Is it the number of calories that healthy calories they receive in their diet, or is it the number of hours they spend studying? And I can say, well, for a 1 hour change and for a 1 calorie change, well, those are on such different scales that we don't even know how we could compare them to each other. But remember, these are parametric statistics. They assume that the distribution of these variables is normal. And so we can talk about a certain normal spread under the curve. Not talked about in this video series, but it's the basis of inferential statistics. So with a little exploration, you can figure out what that's talking about. But under the normal curve then, we have areas that can be defined in standard deviations. Well, what we have over here to the right is we have the standardized slopes. These are called betas, where the unstandardized slope was a lowercase b. The standardized slope is a capital B, or it's called a beta. Now, I'll admit that I have seen stats programs monkey around with all of these terms, and it gets kind of hard to know how to predict for you what to call them. So this program just calls them the unstandardized slopes and the standardized slopes. That's probably safest. But the most common use and almost universal use of the word beta is to talk about a standardized slope. Now we're talking about something different. Now, for these standardized slopes, here's how you would read it. It's not for 1 unit change in the original units. Now it's for 1 standard deviation increase in this independent variable. After controlling for the effects of the other independent variables, the dependent variable will change this amount, the beta, standard deviations. So this assumes you understand what standard deviations are. This assumes that you understand what it means to have a statistical control taking away the effects of something. There's a lot of layers to this. But even if you don't understand all the layers, can you tell me which of those numbers is bigger and which is smaller? Ignore the sign. The sign is just the direction of effect, and it doesn't affect the magnitude. It doesn't tell us the magnitude of effect. It just tells us the direction of the effect. So one of them is a 0.227. One of them is a 0.580. So you can see that HDI matters more because it's all turned into standardized units. It's all in standard deviations, and we're assuming that there's a normal curve involved. So standard deviations, while they differ in actual amount from distribution to distribution, they always capture the same proportion of area in the distribution. So now we're talking about for 1 standard proportion of units, right, 1 standard area under the curve in the independent variable, what will happen to the dependent variable? Well, for government spending, for a 1 standard deviation increase in government spending, after controlling for differences in the country's HDI values, you will see about a fifth, 0.23, or maybe call it about a fourth, of a standard deviation change in the percent of the population saying that prostitution is never justifiable. It's not a 0.227 percentage points in the percent of the population. It's 0.227 standard deviations. If you wanted to, you could go back and look at the distribution of the percent of the population indicating that prostitution is never justifiable, and you could find the standard deviation. This is 0.227 of that many percentage points reported in that standard deviation. But practically speaking, you just look at this and you say, government spending has an effect where for one standard deviation increase in government spending, you'll see about 0.23 standard deviation increase in the percent of the population saying prostitution is never justifiable. Whereas for Human Development Index scores, for one standard deviation increase in HDI, a country will see a decrease of over half a standard deviation, 0.58, over half a standard deviation in the percent of the population saying that prostitution is never justifiable. We can also note that the government spending result is not significant, that 0.227 is not a big enough effect for us to say we reject the null claim that basically the beta in the population might really be zero. But the result for HDI is statistically significant. 0.58 is a big enough effect that we're comfortable saying that we can reject the idea that in the population the beta is really zero. Okay. So how do we use these results to describe the patterns, to provide the evidence? What we want to do is we basically want to write up the results for each independent variable, the shape, strength, and significance as found in these two tables. And then we identify which independent variables do or don't matter. So we'd start by saying that we only need to look at the standardized slopes and the p's in the regression results. And I've also grayed out the correlation for GDP per capita because it wasn't included. If we look at government spending, in the original bivariate results right here, it was very strongly related, and it was a statistically significant relationship with percent of the population saying prostitution is never justifiable. But now, after controlling for HDI values, now it's a much smaller effect. This is on a scale of 0 to 1, so we can really talk about very strong here. This one, it gets a little murky and it's hard, and I can't give you clean thresholds, but you can clearly think that, 0.6 is a long ways up from 0, but 0.23 when you have 0 as the bottom, and most betas land below 1. Sometimes they'll go a little bit over 1. If you start getting betas that are 2 and 3 and 4, there's probably something very wrong in your model. You probably have multicollinearity is oftentimes what's happening. But if we look at it that way, then we can say 0.227 is quite a bit lower than 0.6. The effect went down. It's still positive, but it was larger and it was significant, and now it's quite a bit smaller and it's not significant. Whereas the value for HDI, after controlling for government spending, went from a negative effect that was very strong and significant to a negative effect that was still fairly strong and significant. So controlling for government spending didn't make a really big change in the Human Development Index effect. Controlling for the Human Development Index effect had a pretty big effect, a notable effect on government spending. And so we can write that up. We could write up for government spending, what did we have in the original bivariate? We had a strong, positive, significant result. And what did we have for the multivariate result after controlling for HDI? And we had a weak, positive, not significant result. And you see then controlling for HDI made a big difference in how much we think government spending matters. When we do it for the HDI, we say HDI originally had a negative, very strong, significant result in the Pearson's R, and after controlling for government spending, it still had a strong, significant negative effect. So the control had less effect. Now, if we were going to go another step further, we could actually begin to use that information to understand where HDI and government spending need to fit into a causal model such that changing such that controlling for each other has this effect. There are ways to take these results and begin to specify a causal model. It's just intriguing enough. I almost want to launch into it, but that's not the intent of this video series to do. It's simply saying which of these matter more. Well, HDI matters more. So after we've written up a description, a comparison of the bivariate to the multivariate for government spending, and for HDI, the bivariate to the multivariate, then we end up saying HDI still matters after controls, and government spending does not matter after controls. Now, collective effects. So in linear regression, you get three tables reported to you. One of them is the net effects, and generally speaking, it's where most people want their answers because they want to figure out which independent variables actually matter after controlling for the others, and which ones are the more important independent variables for trying to understand how life works. Collective effects does something else. There isn't much here to work with. You see a lot of numbers, but that ANOVA table in the middle with regression, residuals, sum of squares, degrees of freedom, mean squares, the F ratio, that's the same thing we've seen in other tools. We saw it in bivariate regression. We saw it in what is more commonly called ANOVA, or one-way ANOVA, two-way ANOVA, factorial ANOVA. All of them basically try to compare the amount of variation that is now explained knowing an independent variable and the amount of variation that is still not explained in the dependent variable by knowing the independent variables. In this circumstance, what we're doing is we're saying how much of the variation in the dependent variable have we now been able to explain using the whole set of independent variables. So we have two independent variables here. How much does the pair of them help us to explain? So we have what's called the multiple correlation coefficient, and just like we could with little r, we squared little r in correlation and we called it the coefficient of determination. Here we square capital R, the multiple correlation coefficient, multiple correlations because there are multiple independent variables. And now we square it, and we can again read this just like we would read eta squared or little r squared. It's just called the multiple correlation coefficient squared, or multivariate r, multiple r squared. And it tends to overestimate a little. So 0.581. Should you report 0.581? It's fine. Most of the time, these two numbers, the r squared, multiple r squared, and the adjusted multiple r squared, are very close to each other. 0.58, 0.55. Would you draw wildly different conclusions saying 58% of the variation in percent of the population with this view of prostitution is explained by these two variables, as compared to 55% of the variation in view of prostitution is explained by these two independent? Not really. So adjusted r squared is the recommended choice, but if the numbers are really small, you can actually get a negative adjusted r squared, which tells you that now you're in the land of delusion. So r squared is fine. If you want to work with adjusted r squared, it's fine. Report whichever you like. But most practitioners now use adjusted r squared because this overestimates the strength just a little bit. Okay. This, for the F value, is the p-value that gives us the statistical significance of F. It is also the statistical significance of this collective result. So for collective effects, all you end up doing is reporting a multiple r squared, saying this is the proportion of variation explained, or if you want to call it a percent, call it 58% instead of 0.58 proportion. 58% of the variation in view of prostitution is explained by just using these two independent variables, government spending and HDI value. And it is a statistically significant result. You get strength and you get significance, and that's all. There's no shape. R squared can never be negative. I said that adjusted r squared could be negative, and I said you're entering the land of delusion. No squared number can be negative. It's not possible for a squared number to be negative. So the adjustment process, if it's done on a really small r squared, leads to strange results. So how do I write up these results? I just say 58% of the variation in percent of the population that believes prostitution is never justifiable is explained by knowing countries' government spending levels and knowing countries' human development index levels. This is a statistically significant result. That's it. So there are other things you can do with this. You can actually run this multiple R squared and then add another independent variable and see what it changes. And then add another independent variable. So it's actually possible to say, well, we explained, let's say we had two independent variables and we explained 15% of the variation in the dependent variable. Still worth noting, we explained 15%. This 58% is amazingly large. But let's say we explained 15%. Then we could say, well, what if we added another independent variable and it went from 15% to 39%? We'd say, well, that variable mattered a lot when we added it. So this kind of keeps score as we add independent variables. You have to run the analysis, then rerun it with another independent variable. In this circumstance, we might be interested to run this result just for the bivariate, looking at the HDI values. We did that actually in a previous video, and you could go back and look at it. But the question is, did adding government spending, knowing that controlling for HDI made government spending not matter very much and not be a significant result? Maybe it's possible that most of that 58% of explained variation is all due to HDI, and we don't even need to have government spending in the model. So you hear how we're working towards specification of which variables matter and belong in the model. Multivariate regression is the end of this video series, and we've walked through everything from using categorical univariate to scaled multivariate. Hopefully the different tools available to you can help you to answer the practical questions wherever you are and whatever you're working on.